Hello everyone, I'm glad to present our work at this WebRTC conference. This is Yongjae, and today's topic is sharing ambient objects using real-time point cloud streaming in web-based XR remote collaboration. I'm a research assistant at the Korea Institute of Science and Technology and have been studying web-based XR collaboration methodology since 2016. Our topic is covered by this sequence: motivation, previous works, our approach, implementation, and conclusion. Recent advancement in hardware and vision technology has made extended reality become more practical and more popular. Probably one of the most actively used XR applications is remote collaboration. This is because it allows more intuitive information delivery by displaying visual information instead of using speech or writing. Moreover, in remote collaboration, it is important for a user in a local site not only to receive information from others, but also to give them information about the local environment. To accomplish this, a variety of methods to share a local environment with remote users have been suggested, such as video sharing or mirrored 3D world. However, these methods have some drawbacks. Information drawn on display is sometimes too abstract to understand. Besides, a complicated hardware configuration is required to imitate the real world, or a lot of advanced preparation is required to make 3D resources before the collaboration. Our proposal is built on XR collaboration system, where users can share their environment in rich information and on the spot. Next is previous works. In the last WebRTC conference, we had introduced unified representation for XR content and its rendering method. In there, we devised special HTML tags that is representing the XR entities, which are called the revised XR tags, in short WXR tags. Authors can make an XR content by compositing these tags, and the content can be run on both AR and VR devices without any specific modification of the content. This cross-device execution is accomplished by a special XR renderer, which is called the WXR renderer. This renderer chooses a distinctive rendering strategy according to the currently selected XR mode by users. Consequently, with the WXR text and the WXR renderer, people can literally create and consume XR content through the web. In addition to that, we have devised the concept of the unified coordinate system, which is a method to locate the pose of an AR camera in the VR coordinate system. In there, we introduced a special marker called the space marker, serving as an indication for a static point in an AR space. The space marker enables distinguishing the movement between an AR camera and other normal AR markers. This method ensures that users robustly find the AR user's location. Even camera tracking systems such as SLAM or visual odometry don't work. This idea is included in the published research paper, XR Collaboration Beyond Virtual Reality Work in the Real World. Sharing local environments helps remote users to understand the context of the local site. There are several ways to attain this. One of those is using a live streaming. In this method, a local user takes and sends live video of their environment by using an AR camera, and remote users watch this video in VR. This method allows that the local user directly shows their environment to remote users. However, the weakness of this method is that the remote users cannot interact with the environment. They only can point or direct the way to an object in the environment. Another way to share the local environment is making a replica of the local environment before collaboration begins. In this method, remote users dive into VR and interact with the virtually copied local environment. One drawback of this method is that the pre-constructed 3D model does not reflect changes of objects in the local environment once after they are made. Thus, systems adopting this method are only available when both local and remote users work on virtual things, not physical ones in the local. Some research exploits these aforementioned methods to complement the drawbacks of each method. In remote collaboration, real-time data exchange is essential. WebRTC is an effective means to build a reliable, expandable, and low-latency service on the web. Already in the market, commercial products using the WebRTC have been heavily emerging. Next is our approach. We propose a system that enables local users to share their local environment with remote users in real time. This system is based on the web-based XR collaboration system, which is introduced in our previous works. This previous work enables collaborative users intuitively communicate through XR entities of their working targets. However, in this previous system, no way of impromptu sharing local users' surrounding environment is served, so resources representing the local environment should be prepared in advance, like as VR background videos or images or pre-constructed 3D models. Thus here, we add functions sharing a local user's environment to the previous system. Firstly, we conceptualize the world by two things. Those are the object of interest and the ambient object. The object of interest, shortly OOI, is a target that users work on, and the ambient object, shortly AO, is an object except for the OOI. Additionally, we assumed that OOI have frequent movement and that AOs are always static. This assumption is valid particularly in collaboration, because fixing something always entails a physical adjustment of its state and other things remain unmoved, since it is our collaboration objective. Defining this concept, we can easily figure out which object should be shared as a collaboration target or which object should be shared as a local user's environment. The environment sharing process is divided into three stages. The first stage is point cloud reconstruction. In this stage, we use a LiDAR sensor to gather depth information of the local site, then restore the 3D position of the depth points. The next stage is filtering out obstructive points from the point cloud. The final stage is splitting the point cloud into a couple of fragments and sending them to other users by the WebRTC. For sharing local users' environment, we choose point cloud as the medium, rather than 360 image, because in 360 image background, the users cannot reach the ambient environment object. This video illustrates this limitation. The left side shows a remote user experiencing a 360 image and the right side shows him experiencing a point cloud for the same local environment. We can check that the glass wall, window, and chair in the background are still in the distance, even though the user is moving forward. In addition, it looks that the virtual environment comes to the user when he moves forward. Conversely, on the right side, every object becomes closer or farther relative to his movement. Furthermore, it seems that the virtual object is floating in the air in 360 image background. Contrarily, the model looks light upon the table in the point cloud background. The point cloud reconstruction process is quite simple. We recovered 3D positions of points from a LiDAR depth map by using the PNO camera model and a triangle resemblance. Before the point cloud, which we got just ago, is joined to the entire point cloud, we should remove points that disturb the virtual environment. These points are generated from the surface of OOI and screen the 3D model of OOI, making it difficult for the users to recognize the model. This 3D model should be recognizable for remote users to give instructions to the local user, but it is quite difficult because the model is obscured by the points. Moreover, if the OOI moves, the points remain after images and consequently mess up the virtual space. Because the OOI is the target to work on, its movement frequently occurs. Thus, these after images are inevitable, and so we should mask out these points. The masking process is detailed here. By the unified coordinate system, a virtual camera's pose aligns with the physical camera's pose. And to augment a 3D model of an OOI, the field of view of the virtual camera is matched with the field of view of the physical camera. Considering these things, it can be seen that the appearance of the OOI reflected on the physical camera and the virtual camera is identical. From this fact, we can remove the points representing the OOI by checking if the points are within the OOI's area in the screen space. The check is proceeded using the depth buffer of the 3D model render. The depth buffer is also known as G-buffer, and each value in the buffer is called G-value. We define here the range of G-value as 0 to 1 inclusively, and the default of G-value as 1. Note that although we theoretically define the range and default of G-value here, these are also the same as the value defined in the graphic libraries such as OpenGL and Direct3D. When we look at the pixel at the lower right corner in the rendering image of a 3D model, it has the G-value as 1 because the pixel is outside of the OOI. So we can determine that those points which are rendered at the pixel are not representing the OOI. However, in the case of the pixel at the center of the rendering image, that pixel's G-value is 0.999 approximately. Thus, we can determine that those points which are rendered at the pixel are representing the OOI. Based on this determination, we just discard those points. This determination is conducted for all pixels in the rendering image and repeated on each frame of point cloud reconstruction. As a result, we can obtain a clean point cloud accepting the points representing OOI. Moreover, because the point cloud reconstruction is still working, as the OOI is moved, at the same time new points are formed at the newly revealed areas. You can find the information in the right video. As the cyan flange model moves to its left, the hole on the desk is filled with the newly generated points. Note that this masking process is very efficient because it proceeds at the fragment shader level rather than the vertex shader level. In the last stage, the masked point cloud is sent to remote users through the data channel of WebRTC. For practical reasons, this channel has limited data capacity that can be sent at once. Thus, we should divide the point cloud into a couple of massive packets. Before dividing, what we need to know is that color and vertex buffers are separately managed for the purpose of efficient memory access. If these points are sent in the sequence stored in the memory, packets containing color information and packets containing position information depend on each other. Because the points are rendered not until both color and position information are available, a delay happens until a dependent is arriving. This issue can be resolved by reordering the data. By interweaving the color information and position information of the points in one packet, it is possible to prevent dependence from occurring. As a result, the remote side renderer can draw the points as soon as they arrive. I will then move on to prototype implementation. As I mentioned, the proposed system is based on our previous study, so the architecture is similar at some level. The mainly improved part is those related to the environment sharing feature. The AR engine module on the local user side tracks OOIs and scans the local environment with LiDAR. In our implementation, we use the AR kit here. The generated depth map from the AR engine module is passed to the point cloud generator module to process it into reconstructed point cloud. The OOI masking stage is also conducted in this module. Then, the masked point cloud is passed to the point cloud streamer module, in which the point cloud is split into pieces of a message and delivered to remote users. This video demonstrates our implementation. The upper left shows a remote user and the lower left shows a local user, and the right side shows a third-person view of the user's collaboration. In this collaboration, their task is disassembling the ball valve which is in the center of the local site. This means that The OOI is the verb and the AO is the surrounding of the local user. Before starting the collaboration, the local user looks and scans around briefly. By doing this, the remote user can understand the local user's context. Note that due to the OOI masking, a hole is made under the OOI. Later the OOI is moved. In this case, the verb handle is rotated. This hole is exposed to the LiDAR and filled with the new points. And also we can see the remote user recognize the existence of the scanner in the local site and entice the local user to use it. In conclusion, in this presentation, we propose a new concept that distinguishes object of interest from ambient objects in XR collaboration, and filtering out the points representing OOI from reconstructed point cloud using 3D model of OOI, and an efficient data structure for transmitting point cloud under WebRTC communication. In the future, we further do conduct a quantitative user survey to verify the efficiency of using the suggested XR collaboration method. This was Yongjae from KIST, and I appreciate your listening. Thank you.